just go over it. So let A be this matrix A11, A12, A21 and A22. So the determinant of A would be given by this expression, and the determinant of A plus I upon calculation gives rise to this expression. So first we'll prove it in the forward direction, that determinant of A plus I is equal to determinant of 1 plus determinant of A. It means that the trace is 0. So simply determinant of A plus I is equal to determinant of A. If we compare both these expressions, we find that it means A11 plus A12 is equal to 0, which implies that the trace is 0. Now in the reverse direction, if trace is 0, then these two expressions are equivalent. So if trace equal to 0, the determinant of A plus I is given by this expression, which indeed is equal to the determinant of A plus 1. So we have proved it in both ways, like if trace is 0, then this condition holds true, and if this condition holds true, the trace is 0. So that was an important concept that we should keep in mind when trying to prove any such if and only if condition. So again, I don't see any doubts, so I'll move on to the next problem. The next problem was just a simple problem. It's just a use of row transformations and all that. So we have an n cross n real matrix with the property that all the entries in each row add up to 0, sorry. So we need to show that the determinant of A is 0. So I've used the thing that the determinant of A is equal to determinant of A transpose, and then we do the row transformations on A transpose, which is equivalent to doing transformations on the columns of A. But we always talk in terms of transformations of rows. That's why it's easier to visualize by doing this step. So in the matrix A transpose, we get that the sum of, like if we sum them, the nth row will be like row 1 up to row n will give us the 0 vector. So it can be written that row n is the sum of row I, where I goes from 1 to n minus 1, and we take the negative of this. So we simply do a row transformation, like we add row 1 plus row 2 up to row n minus 1 to row n. So row n will become a row of zeros. And if we expand it by that row, like it's just expanding, it means that we are expanding by a row of zeros. So it will give us 0. So similarly, you can do it with any row, like instead of row n, do it with row 1 or row 5 or anything like that. It's just a simple problem. It is also like separation rule in question 6. Question 6. Question 6 of the practice problems. Okay, I'll come back to this later. You can ask it later. So next question we have that given that adjoint A is given by the cofactor A ka transpose, we need to show that if A is an n cross n invertible matrix, then determinant of adjoint A is given by determinant of A raised to power n minus 1. So determinant of A is a scalar quantity and we raise it to the power n minus 1. So it's just the use of some properties that are discussed in class and we just bring them together. So we have proved that A into adjoint A equals determinant of A times the identity matrix. So take determinant on both sides because the determinant function, like it's unique, like for same it will give same value. So determinant of, it's a function basically, determinant of A into adjoint A is same as determinant of A into identity matrix. So using the property that determinant of AB is equal to determinant of A into a determinant of B, we get determinant of A times determinant of adjoint A is equal to determinant of A raised to power n. So from here, what we have is, instead of having one, like we have a scalar matrix in which all the elements on the diagonals are equal to determinant of A. So if we take its determinant of this matrix in which all the diagonal element values is equal to determinant of A and the remaining elements are 0, its value will be determinant of A power n, and we know that A is invertible. So determinant of A is not equal to 0. So we can easily cancel out one power to get determinant of adjoint A is equal to determinant of A raised to power n minus 1. Okay, so I'll move on to the next problems. Yeah, so this is like the first practice problem was that we have to find the determinant of these like matrices that had some pattern in them. So the first part was this kind of matrix, like instead of having an identity matrix in which from like the top left to the bottom right diagonal we have ones, on the other diagonal we have ones, and all the other remaining elements are 0. So one way to do this would have been to do induction or something like that. That would have also given us the desired results. But the other way to think about this is by doing row transformations, we transform this matrix into I, like similar to Gauss-Jordan method. So if n, consider the case n is even. So how do we transform this matrix to I? So if you exchange row 1 and row n, so we get 1 at a11 and 1 at ann. So the first row and the last row are similar to the rows of the identity matrix. Similarly, exchange row 2 and row n minus 1, row 3 and row n minus 2. So basically, generalizing it, row I is exchanged by row n minus I plus 1, like put I equal to 1, so row I goes to row n and so on. So row n minus 2, since n is even, n minus 2 will be a number, so n minus 2 goes to n minus 2 plus 1. So basically for row 1, row n exchange them, row 2, row n minus 1 exchange them, and so on, row n minus 2 to row n minus 2 plus 1 exchange them. So basically we are doing n by 2 exchanges, and each exchange will like change the in that alternating property of the determinant function, each will multiply it by -1, like whatever the value is of this matrix, the matrix will become -1 times this value. So we are doing n by 2 exchanges, so -1 times n by 2 of the final matrix, and the final matrix is the identity matrix, so we know that its determinant value is 1. So the final answer is -1 raised to power n minus 2. Similarly, if n equal to odd, so the middle row, like n, so if n equal to 5, so row 2, then if n equal to 7, then row 4, then or something like that, like n minus 1 by this row will be the row, like its position need not be changed, and for all the other rows we'll have to exchange their positions. So like, okay, so if we label the rows as 1, 2, 3, 0, 1, 2, 3, 4, then n minus 1 by 2 would work as stated here. Otherwise, you'll have to do n plus 1 by 2. So that many exchanges are required. So for example, in 3, like n minus 1 by 2 exchanges will be required, but like the row n plus 1 by 2 won't be changed. Like for consider n equal to 3, so you exchange row 1 and row 3. You don't do anything to row 2. So one exchange is made and the second row remains as such. Similarly, when n equal to 5, row 1 and row 5 are exchanged. row 2 and row 4 are exchanged and nothing happens to row 3. So 2 exchanges are done. So basically n minus 1 by 2 exchanges are done and the n plus 1 by 2 towards row remains as such. So similarly, after n minus 1 by 2 exchanges, the matrix will get transformed into an identity matrix. So the value of the determinant will be given by this expression. Now, the last problem that I would like to discuss is the C part. It was also a similar problem, like we had given a matrix which had some pattern in it, and we need to find the value of its determinant. So for let's see some examples. For n equal to 1, the determinant value is 2. For n equal to 2, we have this 2 cross 2 matrix, and if you calculate, its determinant will come out to be 3, and do the manual calculation for n equal to 3 and you get 4. So now you open it. So basically we get this recursive, like this, what do we call this, recursive formula, like determinant of n, like the determinant of an means a matrix that is follows this pattern and it is of dimension n cross n. So determinant of an is 2 times determinant of an minus 1 minus determinant of an minus 2. Now how did we get this? I'll just quickly go over it. You have this matrix, you open it along the first row. So we just need to open it using first this a11 and a12 because all the other elements are 0. So for a11, what do we get? We have this 2 multiplied by the determinant of this n minus 1 cross n minus 1 matrix. And if you see carefully, this is basically an minus 1. So we get the first term from here, 2 times determinant of an minus 1. And now if you open along this, the second term we get by opening along a1, comma 2. So minus 1 will be multiplied by minus 1. So basically we get a 1 here. And then we need to calculate the determinant of this n minus 1 cross n minus 1 matrix that is found by deleting the first row and the second column. So now what we do is that if you just try to visualize, just have this matrix, remove this column. So we don't see an minus 1 or anything else right away. So we open this n minus 1 comma across n minus 1 dimension matrix. So if you see the first column, it will be minus 1 followed by all zeros. So just open along the first column. So this minus 1 will get multiplied by the determinant of this n minus 2 cross n minus 2 matrix, which is basically an minus 2. So if you observe carefully, we get this formula, like just opening it twice, first along the first row and for the second element, you open it along the first column and you get this formula and you just unroll this recursion, like write determinant of n minus 1 in terms of determinant of n minus 2 and n minus 3 and then so on, you will get the final answer. So that was the I'll just stop.